linear algebra student, this video is for chapter 5.1 part 3. We just want to talk about theorem 2. We don't have enough time in the last video, so we just want to talk about it. In terms of the calculation part of 5.1, I think part 1 and part 2 is sufficient. So this is introducing to you some characteristics of eigenvalues and eigenvectors. See, theorem 2 said that if you have n distinct or r distinct eigenvectors corresponds to r distinct eigenvalues, then v1 to vr are linear independence. Now, between the same eigenvalues, eigenvectors are always independent. So actually, if you group all the eigenvectors together for a matrix, they are all independent. So, but for this proof, we are assuming that otherwise. We're assuming that Vp plus 1 is not independence, and it depends on V1 to Vp. So I can say Vp plus 1 is actually equal to C1 V1 plus C2 V2 plus all the way to Cp Vp for some non-zero, for some C1 to Cp. So V plus 1 can be written as a linear combination of them. Now let's multiply this whole thing by A. If I do A Vp plus 1, it would be equal to C A V1 equal to C2, C1, A V2, right? So equal to Cp A Vp. And because all of them are eigenvectors, so A Vp plus 1 become A lambda Vp plus 1. Oh, well, actually, this corresponds to lambda P plus 1. And, oh, no more A. Erase this first. Because AVP plus 1 is just lambda P plus 1, Vp plus 1, right? This will be C1 lambda 1, V1 will be C2 lambda 2, V2, all the way to Cp lambda P Vp. So this is equation 1. And I'm going to also multiply lambda P plus 1 to this one. So multiply this both sides by lambda P plus 1. I will have lambda P plus 1, also Vp plus 1. But it will be C1 lambda P plus 1 because I'm just multiply this whole thing by lambda P plus 1. Right, so every single one will be V2 lambda P plus 1 V2 all the way to Cp lambda P plus 1 Vp. So but they're actually, so this is the second one. If I subtract them, this would be 0, right? These could be factored out as C1 lambda 1 minus lambda P plus 1 V1 C2 lambda 2 minus lambda P plus 1 is always P plus 1 because that's what we multiply. And then V2, etc., etc. So that actually that means Cp lambda P minus lambda P plus 1 Vp. So that means this shows that V1 to Vp are dependent, right? Which is a contradiction. So we can say that the whole thing is actually linear independence. So you can read the book but this is just a proof, so you don't understand, it's fine. But that shows you that if the vectors are from different eigenvalues, they're distinct, then they are independent. Example 8. So let's just investigate this. So this is A that we know. Later on, we'll talk about how do you know it has 3 eigenvalues. Given that we know that there's 1, 4, negative 3 as an eigenvalue, shows that the eigenvectors are independent, so that the I think the corresponding eigenvector, because we have 3 different ones. Each one of them has one eigenvector, so show that they're independent. So let's say, well, actually, I know it is 1, 4, -3 because this is a diagonal matrix, so it's very easy. But actually, find an eigenvector. So lambda equal to 1 first. So I would have to solve a minus 1i x equal to 0. That means I'm going to do the augmented matrix of minus 1, minus 1, minus 1. That means 0, 6, 2, 0, 3, 5, 0, 0, minus 4, right? And 0, 0, 0. To solve this, what is the solution? Let's see. Do I have it? Oh, yeah, I have it here. 0, 6, 2, 0, 3, 5, 0, 0, -4, 0. Right? So if I do RLEF of C, what do I get? I get 0, 1, 0, 0, 0, 0, 1, 0. And then that's it, 0, 0, 0. So x1 is the free variable. So that would equal to 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. The prefix position is this and this. So x1 is free, right? So that means x1 and then 0 and then 0 is an eigenvector. So it's x is equal to that. So that means 1, 0, 0 is a when x1 is equal to 1 is a eigenvector. For lambda equal to 1, let's do lambda equal to 4. Ooh, do I have enough space? And let's do lambda equal to -3. So for this one, for lambda equal to 4, I would say a minus 4i. X is equal to 0. So I have to do -4, -4, -4. So that means my RREF is -3, 6, 2, 0, -4 is 0, 5, -4, -4, -7, right? So RRE, 0, 0, 0. I want to solve x equal to 0. So -3, 6, 2, -3, 6, 2, 0, 0, 5, 0, 0, 7. So if I do REF of D, it is 1, -2, 0, 0. 1, -2, 0, 0. 0, 0, 1, 0. 0, 0, 0, 0. Okay, so that means x1 is equal to 2x2. x3 is equal to this one. x3 is equal to 0. x2 is free. So let's assign x2 equal to x2. x2 equal to 1, so one of the vector would be 2, 1, 0. Right? So we have two of them, 1, 1, 0, 2, 1, 0. What about lambda equal to -3? So I have to solve a plus 3i x is equal to 0. That means I'm going to add 3 in all of them. So F3, F3, F3. Okay, so 1 F3 is 4, 6, 2, 0, 4 F3, right? 4 F3 is 7, 5, and 0, 0, -3 F3 is 0. So after 0, 0, I always forgot this. So RLEF can become 4620, yeah, I have 4620, 07500, REF of E equal to 10, -4/7. 01, 5/7, and then 0000. So what is one of the factor? One of the factor would be x1 is equal to 4/7, x3 x2 is -5/7, x3. So one vector would be 4/7, -5/7, and 1. So let's look at this 3 vector. 1, 0, 0, 2, 1, 0, 4/7, -5/7, 1. So are these independent? Yes, because this is already in RLEF. We have prefix position in every row. So they are, by IMT, they are, the determinant is not 0, but by the inverse matrix theorem, these vectors are not are independent. So all the eigenvector that we get from individual lambda would form independent sets of vectors. Okay, so after this, come here. So the first part is to solve lambda equal to 1. What are the vectors? This is the vector. Second is lambda equal to 4. Solve this. This is the vector. And lambda equal to -3. Solve it. This is the vector. And the last part is check that these are linear independence. So that's all for this theorem, theorem 2. But I think it is a good practice to see how, if you know the eigenvectors of the whole thing, you can actually do these steps to find all the eigenvector. And then it turns out that you can use it as a base for R3 because they are all independent and you have 3 prefix position. That is all of 5.1.